Hello lovers, in this video we're going through everything you need for your OCR Gateway Chemistry Paper 1, and this is to a grade 9 standard. Now we've gone through absolutely everything, we've not skipped anything here, so what you can do with this is use the timestamps in the description down below to jump to the bits that you want to. Then you can go to the website, try the predicted papers and the walkthroughs of predicted papers.
The three states of matter can be represented by a simple model which uses small solid spheres to represent the particles. You can see that in the solid we've got this regular pattern, whereas in a liquid, although the particles are still touching, they're in a random arrangement, whereas in a gas they are in a completely random arrangement, far apart and not touching. So we know that going from a solid to a liquid is the process of melting, a liquid to a solid is freezing, whereas going from a liquid to a gas is boiling, and a gas to a liquid is condensing. All of these changes are examples of physical changes. They're not chemical changes because no chemical reaction is taking place. These are simply physical changes. There are some limitations with this simple model, which uses these small solid spheres to represent the particles though. Our first issue is that it doesn't show any forces between the particles. Secondly, all of the particles are represented as spheres, which is an oversimplification. And finally, they show that all the spheres are solid, and we know that they're not, they're actually mostly empty space. So those are our issues with this simple model. This table here nicely summarises the difference between solids, liquids and gases. In a solid, the particles are in a regular pattern, very close together and vibrating around fixed positions. Whereas in a liquid, the particles are randomly arranged but close together and they move around each other. And finally, in a gas, we have a random arrangement, the particles are very far apart and they move quickly in all directions. Make sure you can draw all of these diagrams. Here we're going to have a look at the development of the model of the atom through time. So we started off with Dalton's model. Dalton's model told us that the atom was a solid sphere, cannot be created, destroyed, or divided into any smaller parts. Now, different types of spheres made up different elements, but this sphere did not contain any protons, neutrons, or electrons. Now, over time, J.J. Thomson came along and proposed a new model called the plum pudding model. Here he said that the atom is not actually a solid sphere. What it actually is a cloud of positive charge with negative electrons embedded within it. Next came along the nuclear model, and the experiment that determined this was Rutherford and his students' alpha scattering experiment. Now what Rutherford and his students did was he fired alpha particles at a thin sheet of gold foil. Now if the plum pudding model was true, we would expect all of these alpha particles just to bounce back. However, most of them passed straight through. Some of them were a little bit deflected, and very, very few came straight back. Now what this told us was that the mass of an atom was actually concentrated in a central nucleus, which had to have been positively charged to have repelled this positive alpha particle. And most of the atom actually was empty space, completely contradicting the plum pudding model. And we know this because most of these atoms went straight through the gold foil with no deflection. So over time, Bohr came up with the electron shell model. And the electron shell model told us that rather than just randomly floating around the nucleus, the electrons were actually found in fixed distances from the nucleus, orbiting it in shells. Later experiments found that the positive charge of any nucleus can actually be subdivided into a whole number of smaller particles of equal charge. These were named protons. Finally, James Chadwick carried out some experiments that provided evidence to show the existence of neutrons in the nucleus. And this more or less brings us to our up-to-date understanding of the atom. What is an atom? An atom is the smallest part of an element that can exist. atoms of an element are represented by a chemical symbol, and these symbols will always start with a capital letter and consist of one or two letters. As you can see here, oxygen is just represented with a capital O, and helium is represented with a capital H followed by an E. Now we need to know how small an atom actually is. Atoms have a radius of about 0.1 nanometers, which is 1 times 10 to the minus 10 meters, and the radius of their nucleus is less than 1/10,000th of that of the atom. So it's about 1 times 10 to the minus 14 meters. We've already mentioned this word element. We need to know though, what is an element? What is its definition? So we need to know going into your exam that an element is a substance made up of only one type of atom. If we look at our periodic table, which we will be given in the exam, you can see that we've got over 100 different elements. All of these different letters or pairs of letters within the periodic table that you can see here is representing a different element. And each of those different elements will have their own unique set of properties. Now, if we link this back with what we said an atom was, the smallest part of an element that can exist, we can see that we can represent an element by showing a substance made of only that type of atom. So here, for instance, I've got an atom of carbon, and the element of carbon is just shown as lots and lots of these atoms in a structure. So now we're going to look at compounds. What is a compound? We should know that a compound is a substance which contains two or more different elements which are chemically combined in fixed proportions. So an example of this could be the chemical reaction that occurs between iron and oxygen to form iron oxide. Here we should recognise that iron and oxygen are both elements because they're only made up of one type of atom, whereas iron oxide is a compound. You can see it's made up of two different elements, the iron and the oxygen, which have become chemically combined. Now, it's important that we know that compounds actually have different properties from the elements that made them. So the properties of iron oxide are actually very different to the properties of iron and of oxygen. Now, we also need to know that compounds can only be separated into elements by chemical reactions. We aren't able to simply separate them using filtration or distillation or some other physical process. We have to use a chemical reaction. Now, chemical reactions will always involve the formation of one or more new substances, such as this example here, where iron and oxygen made iron oxide, and they will often involve an energy change. So quite often we'll observe an increase or a decrease in temperature due to this energy change. In chemistry, we're often going to be asked about chemical reactions. We might be asked to write down the word equation, which would look like something like this. Water goes to hydrogen plus oxygen. However, sometimes we'll be asked to write down the symbol equation. Now, this involves writing down the chemical names for each of these substances. So we know that water is H2O, hydrogen is H2, and oxygen is O2. Now, when we're asked to write down the symbol equation, we will need to balance it. And this is a certain skill. When we want to balance a symbol equation, we need to make sure that we have the same number of each type of atom on each side of the arrow. So on both the reactant side on the left and the product side on the right. Now let's use this as a perfect example to show you how to do this. The first thing I like to do is to separate the reactants from the products by drawing a little line. And then on the left-hand side, on the reactant side, let's count up how much of each type of atom we have. I can see I have 2 H's and 1 oxygen. Now if I do the same on the other side, I can see that I have 2 hydrogens and I have 2 oxygens as well. Now, looking at this, I can see I have the same number of H's on the left and the right. However, I only have 1 oxygen on the left and I have 2 on the right. Now, the way we can balance this is by having more waters on our reactant side. So let's write another H2O there. Now here I can clearly see that I have 2 oxygens. So I would cross out that 1 and replace it with a 2. However, by introducing another water, we now have more hydrogens as well. So we cross out the 2 and we replace it this time with 4 because I had 2 of these H2s. So now, although the oxygens are balanced, the hydrogens are now not balanced. So what we need to do is we need to have more hydrogens on the right-hand side. So let's introduce another H2. Now I can see H2 plus an H2 is going to give me 4 hydrogens. So now the hydrogens will also be balanced. I have 4 on the left and I have 4 on the right. So this means that our equation is balanced. Now let's write this in the way that the examiner would want it. I can see I have 1, 2 waters on my left-hand side. So I'm going to put a big number 2 in front of the H2O. That means that we have 2 waters. So now let's look over on the right-hand side. Here I can see that I have 1 and 2 hydrogens, which means I want to put a big number 2 in front of the H2. And there we have it, we have our balanced symbol equation. Now, in order to write down all of these balanced equations, there's some formula that we really need to know. And this is going to hold throughout the whole of chemistry. We need to know that carbon dioxide is CO2. We need to know that water is H2O. We need to know oxygen is O2. Hydrogen is H2. Nitrogen is N2. Ammonia is NH3. Hydrochloric acid is HCl. And sulfuric acid is H2SO4. If we learn these off by heart, we will have such an easier time in our exam. The atom is made up of 3 different types of particle. So we have protons, which are positively charged particles found within the central nucleus of the atom. Then we also have neutrons, which are also found inside the nucleus of the atom. Neutrons, however, have no charge, and we might see this referred to as being neutral. Now, that third particle found within an atom is the electron. Now, electrons are negatively charged particles, and we don't find them in the nucleus this time. We find them in shells which orbit the nucleus. So you can see all this in our little diagram here. And we have to get very used to these diagrams and being able to label them accurately. This table here summarises all of the facts that we need to know about the protons, neutrons and electrons. We need to know that the relative charge of a proton is +1, the relative charge of a neutron is 0, and the relative charge of an electron is -1. We also need to know that the relative mass of both the protons and the neutrons, so both particles found within that nucleus, is equal to 1. However, the electron's relative mass is really tiny compared to this. We might see it referred to in several different ways, but essentially, the relative mass of an electron is approximately 1 over 2,000, or we may even sometimes see it referred to as just very small. Now, it's important that we know a few key facts relating to this information. So atoms of different elements will all have different numbers of protons. This is part of what gives them different properties. However, all atoms of a particular element actually have the same number of protons. Now finally, if we have a think about the mass of an atom, we can see that the relative mass of the protons and the neutrons is so much more than that of the electrons. And this is why almost all of the mass of an atom is found within the nucleus. In chemistry, we will often see isotopes coming up. Now we need to know what is an isotope. Isotopes are atoms of the same element that have the same number of protons but a different number of neutrons. Here you can see I've got two different isotopes of helium. The helium-4 isotope has 2 protons, 2 neutrons and 2 electrons. However, the helium-3 isotope has 2 protons, only 1 neutron and 2 electrons. So notice here, the thing that makes these isotopes of each other is that they still have the same number of protons, however they have a different number of neutrons. Now let's have a think about the ion. What is an ion? An ion is a charged particle which forms when an atom or a molecule gains or loses an electrons. So here I've got a diagram of a beryllium atom. I can see that it has 4 electrons. Now the beryllium atom can lose the 2 electrons within its outer shell to become a beryllium ion. Now because it's lost 2 of these negative electrons, it has become more positive. Think about it like if you lose a negative thought and you become more positive and happy. That's exactly what this beryllium has done. So because it's lost 2 electrons, it now has a 2+ charge. And this is how we would represent this in an exam. Electrons are found within shells. Now shells can also be referred to as energy levels, so use whichever one you prefer. When we're adding our electrons to an atom, we start by adding them to the innermost shell first. Now we need to know that in the first shell, that innermost shell, we can only add up to 2 electrons. Then in the second shell, we can only add up to 8 electrons. And the third shell, we only add up to 8 electrons again. Now this is going to be really, really important when we're in the exam if we're asked to add the electrons to an atom. So let's use carbon as an example here. Carbon has 6 electrons. Now if we want to add this to the shells, we can remember that we start with the innermost shell first. So with the innermost shell, we know that we can add up to 2 electrons. So we add our 1, 2 electrons to the innermost shell of this carbon atom. Then if you think we have 6 electrons in total that we need to add on, if we do 6 minus that 2, we're left with 4 more electrons. And we know that in the second shell we can add up to 8 electrons. So we can fit all of those 4 in that second shell. And that's what I've done here. I've got 1, 2, 3, 4 electrons in its second shell. Now we can represent this using this diagram. However, we might also see it using this system here, where in brackets we do 2, 4. That represents 2 in the first shell and 4 in the second shell. Now let's have a look at how the atom is represented on the periodic table. Now the biggest number is known as the mass number. The mass number is very important because it represents the sum of the number of protons and the number of neutrons. Now the smallest number of the two is the atomic number, and the atomic number gives us the number of protons within that atom. So much information given just from this periodic table. So it's important that we know atoms have no overall charge. Now that then leads us on to the fact that in an atom, the number of protons, those positive particles, must be equal to the number of electrons, those negative particles. And that's how we can have no overall charge. Now we could be asked in the exam to work out the number of protons, neutrons and electrons in a certain atom. So if we look at fluorine here as an example, I know that that smallest number is the atomic number, which gives me the number of protons. Therefore, I know that the number of protons is equal to 9. Now then we can think about the mass number, which is the biggest number. And remember, we said that the mass number was the sum of the protons and the neutrons. So as we now know how many protons there are, we can work out the number of neutrons by doing 19 minus 9. And that ends up giving us 10. Now finally, we can work out the number of electrons by using the fact that we just said that in an atom, the number of protons is equal to the number of electrons. So using that fact then, we can say that we also have 9 electrons. And it's as simple as that. So let's carry out the same process now for an argon atom. I can see here that the mass number is 40, and I know that that mass number is equal to the sum of the protons and the neutrons. I can also see here 18, the smallest number of the two, is our atomic number. And I also, of course, remember that the atomic number is equal to the number of protons. So now that I've looked at this, I can start to work out how many protons, neutrons, and electrons we have. So because the number of protons is equal to the atomic number, I can say that I have 18 protons. Now I know that the number of neutrons is going to be equal to that mass number minus the number of protons. Therefore, to work out the number of neutrons, I can do 40 minus 18, which gives me 22. So I know that I have 22 neutrons. Finally, to work out the number of electrons that we have, we use the fact that in an atom, the number of electrons is equal to the number of protons. So in this case, I can say that I also have 18 electrons. Sometimes we'll be asked a similar question, but to work out the number of protons, neutrons, and electrons in an ion instead. So here we're asked for a Br- ion. We should understand that in an ion like this, which is negatively charged, we must have more negative particles than we have positive particles. Now remember that electrons are the negative particles and protons are the positive particles. So in order for bromine to have a negative charge in this case, we must have one more electron than proton. We can only have more or less electrons, not protons. That's an important fact. So if we look at this, we can see that that smallest number, the atomic number, is equal to 35. So using our knowledge from before, we know that the number of protons is equal to the atomic number. So we have 35 protons. Now we can see that the mass number here is 80. So to work out the number of neutrons, we use the fact that the mass number is the protons plus the neutrons. So to work out the neutrons, I'm just going to do 80 minus the number of protons, 35, which ends up giving me 45. So here I can see that I have 45 neutrons. Finally, we need to write down the number of electrons. And in order to do this, because we have an ion, we have to use the fact that we said that in this case, because it's Br-, we must have one more electron than the protons. So as we have 35 of these positive protons, we must have 36 of these negative electrons to get that overall negative charge. In chemistry, we need to understand what is meant by a pure substance. So a pure substance is a single element or compound which has not been mixed with any other substance. Now you might find this is a bit different to our everyday language. We might use the word pure as we speak about things such as milk may be pure because it doesn't have any additional substances added to it. However, chemically, it is a mixture of different substances. There's fat molecules, there's water, all mixed together. However, in chemistry, we park that understanding and we now just think of it as that single element or compound that hasn't been mixed with any other substance. So we need to know that pure elements and compounds melt at specific temperatures. And we can distinguish between pure substances and impure substances using the following method. So we want to measure the melting point. Pure substances are going to have a sharp, very defined melting point. For instance, water has a melting point of 0 degrees C. However, impure substances are going to melt over a broader range of temperatures. So if you're ever given a range of temperatures for a melting point, you know that that substance is an impure substance. Relative formula mass is the sum of the relative atomic masses of the atoms in the numbers shown in its formula. Now, if we had a balanced chemical equation, due to the conservation of mass, we would expect the sum of the relative formula masses of all of the reactants to be equal to the sum of the relative formula masses of all of the products. Now, the easiest way to explain this is by looking at an example. So let's have a look at working out the relative formula mass of sulfuric acid, H2SO4. So here I can see I have 2 hydrogen atoms, and the relative atomic mass of hydrogen is 1. So I'm going to do 2 times 1, and then I'm going to do plus, and I can see I have 1 sulfur atom. So I'm going to do 1 times 32, which is the relative atomic mass of sulfur. And then I can see I have 4 oxygens. So I'm going to add on 4 times 16, where 16 is the relative atomic mass of oxygen. Now popping that all into the calculator, I find that sulfuric acid has a relative formula mass of 98. It's important that we know the difference between molecular formulas and empirical formulas. A molecular formula tells us the actual number of atoms in a compound. However, in an empirical formula, this is simply the simplest whole number ratio of atoms in a compound. If we look at this example here, C2H6 as an example of a molecular formula, that is the molecular formula of ethane. However, the empirical formula, we would need to simplify the ratio of atoms. We can see that there's a 2:6 ratio between the carbon and the hydrogen. We can simplify this to a 1:3 ratio. So the empirical formula is CH3. Then we can see we've got C6H12O6. This is another molecular formula. We've got a 6:12:6 ratio. Now we can simplify this ratio, divide them all by 6, and we get a 1:2:1 ratio. So the empirical formula of this will be CH2O. Formulations are something that we actually use all the time. Formulation is a mixture that has been designed as a useful product. So examples of formulations include fuels, paints, medicines, foods, fertilizers, cleaning agents, and alloys. You can see that we have so many uses for these formulations in our day-to-day lives. So we need to know, how do they get made? We need to know that to make a formulation, we need to mix together components that have a particular purpose in carefully measured quantities to ensure that the product has the properties required. What is a mixture? We need to know that a mixture consists of 2 or more elements or compounds which are not chemically combined. So this diagram here shows what a mixture looks like. You can see we have a mixture here of these green molecules and these blue atoms. They are not chemically combined, and therefore we have a mixture. So we need to know that mixtures can be separated by different physical processes. These include filtration, crystallization, simple distillation, fractional distillation, and chromatography. And the method that we end up using, of course, depends on what makes up the mixture. Now, these processes do not involve any chemical reactions and no new substances are made. So let's start by looking at filtration. Filtration is used to separate mixtures of insoluble solids, for example sand, and liquids such as water. As you can see from this diagram, we will pour a mixture of insoluble solid and liquid through some filter paper, which will be sitting in a funnel. The insoluble solid will end up staying in that filter paper because its particles are simply too large to pass through. And the liquid will pass through the filter paper and end up gathering inside our conical flask. Like we said, we would use this method whenever we want to separate a mixture of a solid, which is insoluble, and a liquid. Now let's look at simple distillation. Now, simple distillation is used to separate a solvent from a solution when we want to keep the liquid. So an example of this is we want to produce water from a salt solution. Let's have a look at this apparatus here. You can see that we have a condenser, which is an important piece of apparatus which cools down our gas vapours that will form to condense them back down to a liquid. So let's look at the method here. So the first thing we're going to do is we're going to heat up our solution. You can see we're doing that here using a Bunsen burner. So the liquid part of our mixture will evaporate, becoming a vapour and rising up. Now this vapour is going to pass through the condenser where it's going to get cooled down. But when it gets cooled, the vapour will condense back down to a liquid. This then separates the liquid from the dissolved solid, and we have successfully separated them. Fractional distillation is another method to separate substances. Now we use fractional distillation to separate two or more liquids which have different boiling points. Now this process is very similar to that of simple distillation, with one main difference to the apparatus, and that is the presence of a fractionating column. It's that fractionating column that is key to separating these two liquids. So let's run through the steps here. So the mixture is going to get heated to the temperature of the liquid with the lowest boiling point. Now the liquid with the lowest boiling point is going to evaporate first. It's going to rise up through the fractionating column and pass through the condenser, eventually cooling and condensing. Now when all of this substance has evaporated and condensed, we've separated the two liquids. Now let's have a look at crystallization. Now crystallization is used to separate a dissolved solid, a solute, for example sodium chloride salt, from a solution. So we do this when the thing that we want is that dissolved solid. So at the end of this process, we want to end up with that solid. Let's look through the steps. So the first thing we want to do is to gently heat the mixture in an evaporating basin. Now some of the solvent, for example water, will evaporate away, making the solution much more concentrated. Now we're going to remove this from the heat when the crystals begin to form. We're going to leave it to cool, and then we're going to filter it to remove any excess liquid that there may be. Finally, we're going to leave those crystals to dry. When they've dried, we have successfully separated our solid from the solution. Chromatography is a method that can be used to separate mixtures, and it can be really useful when we want to attempt to identify certain substances. So, as you can see in this diagram, we often use chromatography paper and a pencil line. We put some dyes or whatever substances we're looking to examine along this pencil line and place it into a solvent. This diagram here is actually showing us paper chromatography. There's also TLC or thin layer chromatography, which is a very similar process. The main difference really is instead of using chromatography paper, we might use a glass plate coated in silica gel. Now chromatography uses two different phases that we'll hear about in the exams that we need to be familiar with. So the mobile phase is the solvent, which is going to carry the different substances. This could be water, for example. The stationary phase, on the other hand, is the non-moving phase. In this case, that could be the chromatography paper. And of course, if we were using TLC or thin layer chromatography, the stationary phase would in that case be the glass plate coated with silica gel. So in carrying out this chromatography, we can calculate an RF value that will be used to identify unknown substances. All different substances will have their own unique RF value. So the way that we work out the RF value is we get out our ruler and we measure the distance moved by the substance. So that will be from that pencil line up to the point where that dot has moved. And then we divide it by the distance moved by the solvent. And that again is going to be moving from that line up to the maximum distance that it has moved. And it should make that clear in the exam where the solvent's moved to. So remember, we're just going to use our ruler. Make sure you're consistent with using centimetres or millimetres for both measurements. It doesn't matter which one you choose. And then pop it into the equation and you'll get the RF value, which will always be a number between 0 and 1. Now we need to know that the RF value might change in a different solvent. So if we use water one time and say ethanol another time, we may get a different RF value. So mixtures are going to separate into different spots. So here you can see this shows a mixture because we've got two different spots. However, pure compounds like this one here produce a single spot, and that will be true in all of the solvents. It will always only produce a single spot. Gas chromatography is another type of chromatography, which is a bit different to the thin layer or the paper chromatography. So in gas chromatography, the mobile phase is actually an unreactive gas, for example, nitrogen or helium. The stationary phase is a very thin layer of an unreactive liquid. And what happens is the gas is going to get passed through a column of these silica beads, which are all coated in this stationary phase of the unreactive liquid. And as the gas passes through, different substances found within that gas are going to travel at different speeds because they're going to interact at varying degrees with that unreactive liquid of the stationary phase. Now, because they're moving at different speeds, this means that the time that they take to leave the column is going to differ. If we record this, then we have the retention time. And it's the retention time that we use in gas chromatography to identify what substance we have. So in gas chromatography, we use retention time. In thin layer or paper chromatography, we use the RF value. So if we look at this little graph that I've got here, we can see that there's 3 peaks. Now, because there's 3 peaks, this means that we have 3 different substances. We can find the retention time of each substance by looking at each peak and measuring the time of that peak. So here we can see the retention time of A would be found here. If we look at these different peaks, we can see that the height of peaks A and C are the same. Now, because they're the same height, that means that we have the same abundance or the same quantity of each of these 2 substances. If we were to then look at B though, you can see that B is a much bigger peak, isn't it? It's almost double A and C. So therefore we could say that B has the highest abundance out of these 3 substances found in the sample. So I hope that you can understand the information that we can get from one of these graphs, which can show us retention time and also the relative abundance of the different substances. Once we know the retention time, we can then compare it to a database or maybe information given to you in the exam to positively identify what that substance is. Now we need to know that elements that react to form positive ions are metals, and elements that react to form negative ions are non-metals. Now on our periodic table, we need to know where we find our metals and where we find our non-metals. So let's have a look at it. If we look at this little staircase that we have here, where the staircase starts just above aluminium and goes all the way down, we can see that the metals are on the left-hand side of the periodic table and the non-metals are on the right-hand side of the periodic table. We need to make sure that we can compare the properties of metals and non-metals. Metals have, generally speaking, a high melting and boiling point, whereas non-metals, most of the time, have a low melting and boiling point. Metals, on the other hand, mostly have high density, whereas non-metals mostly have a low density. Metals are shiny and non-metals are generally dull. Metals are good conductors of electricity, whereas non-metals are generally poor conductors of electricity, with the exception of graphite. Metals are malleable, which means they can be hammered into shape, whereas non-metals are not malleable. We need to know why metals are good conductors of electricity. And this is because they have delocalized electrons, which are free to move through the lattice structure. We also need to know why metals are malleable. The reason that metals are malleable is because when a force gets applied, the layers of the ions can slide over each other. In addition to these physical properties, we also need to be able to compare the chemical properties of metals and non-metals. We need to know that metals form positively charged ions, whereas non-metals form negatively charged ions. We need to know that metals, when they react with oxygen, form basic oxides, some of which are able to dissolve in water to form alkaline solutions, whereas non-metals, when they react with oxygen, they form acidic oxides. We also need to know that when a metal reacts with a non-metal, the metal atom loses electrons, whereas the non-metal atom gains electrons. This forms an ionic bond. However, when we have non-metal atoms just reacting with other non-metal atoms, instead the electrons are shared. Now this forms a covalent bond. Here we're going to have a look at a vital part of chemistry, the periodic table. We're going to use this so much throughout the course. So a periodic table, why is it called a periodic table? It's because similar properties occur at regular intervals or periodically. Now let's have a look at this periodic table then. We should know that the columns are called groups and the periods are the rows. So we start with period 1, which is our first row. Then the next one is our period 2, period 3, 4, and so on. Now we need to know that all of the different groups have elements with similar properties within it. Now all of the elements within a group have the same number of electrons in their outer shell. This is such useful information. So for example, all of the elements in group 1 have just 1 electron in their outer shell. All of the elements in group 2 have 2 electrons in their outer shell, and so on. Another great fact to know is that elements in the same period all have the same number of electron shells. So hydrogen and helium in period 1 just have 1 shell, all of the ones in period 2 have 2 shells, and so on. Early periodic tables, like the ones here by Newlands, were incomplete, as many of the elements were unknown. Before the protons, neutrons, and electrons were discovered, scientists arranged elements in order of their atomic weights. However, this meant that some elements were placed into incorrect groups, as their chemical properties were ignored. Now, Mendeleev tried to solve this problem. He arranged elements in columns based on their similar properties. He arranged elements horizontally in order of atomic weight, but left gaps to allow for elements that may have been undiscovered up to that point. In some places, he changed the order of atomic weights to maintain the patterns in the columns. Now, over time, elements with the properties predicted by Mendeleev were discovered, filling the gaps. Now, isotopes explained why the order of atomic weight was sometimes incorrect. And that is how we got to the periodic table that we use today. There are 3 types of strong chemical bonds. We have ionic bonds, covalent bonds, and metallic bonds. We need to know that we find ionic bonds in substances that have metals and non-metals bonded together. An example of that is sodium chloride. Covalent bonding, however, is found when we have non-metal atoms bonded together. An example of that is diamond, which is made up of just carbon atoms. Now finally, we've got metallic bonding. Now that's found in metals. An example of that is iron. Let's take a closer look at ionic bonding. So we've said that ionic bonds form between metals and non-metals. When a metal atom reacts with a non-metal atom, electrons from the outer shell of the metal atom are transferred. The metal atoms lose electrons and become positively charged ions, also known as cations because they're positive. So here, if we have a look at beryllium, which has 2 electrons in its outer shell. Now, beryllium wants to get a full outer shell. This means it needs to lose its 2 electrons. By losing 2 electrons, it ends up as a positive ion with a 2+ charge. And what we find is that all of the group 1 metals form ions with a 1+ charge. The group 2 metals form ions with a 2+ charge, whereas the group 6 non-metals form ions with a 2- charge, and group 7 non-metals form ions with a 1- charge. Well, we've looked at what happens to the metal atom, but what happens to the non-metal atom? Non-metal atoms are going to gain electrons, and they're going to become negatively charged ions, or anions. Let's have a look at oxygen as an example here. I can see here that oxygen has 6 electrons in its outer shell. Now to get a full outer shell, it needs to have 8 electrons in its outer shell. And the easiest way that oxygen can do that is by gaining 2 electrons. If it gains 2 electrons, it becomes a negatively charged ion with a 2- charge. Well, all this leads us to the question, what is an ionic bond? What an ionic bond is the strong electrostatic attraction between these oppositely charged ions. Of course, we're going to end up with that positive metal ion and the negative non-metal ion. After reacting, both that metal and non-metal ion are going to have a full outer shell, and they now have the same electronic structure as a noble gas in group 0. Now we can show the electron transfer during the formation of an ionic bond using a dot and cross diagram. And when we draw a dot and cross diagram, we generally only draw the outermost shell of electrons. Well, let's have a go at looking at the formation of an ionic bond between beryllium and oxygen. So we know that beryllium has 2 electrons in its outer shell. In fact, its electronic configuration is 2-2. Oxygen as well, we just said earlier that we have 6 electrons in its outer shell. So it has a 2-6 electronic configuration. Now what's going to happen is the beryllium is going to give its 2 electrons to the oxygen. We end up with a beryllium 2+ ion and an oxygen 2- ion, and we're going to write them just like this with square brackets around their full shells and the charges up on the top right hand side. Let's have a look at another example here. Draw a dot and cross diagram to show the bonding in sodium chloride. Well, sodium's in group 1, so we know it has 1 electron in its outer shell. Chlorine, on the other hand, I know is in group 7, so it has 7 electrons in its outer shell. I'm representing sodium's electrons with a cross and chlorine's with a dot. You can do it the other way around and it still works. So the sodium is going to give up its electron to get its full outer shell. That leaves us with a 1+ charge ion, whereas the chlorine is going to gain that electron and it's going to therefore become a negative ion with a 1- charge. So I just put a little minus in the top right-hand corner for chlorine. What is an ionic compound? An ionic compound is a giant lattice structure of ions held together by strong electrostatic forces of attraction between oppositely charged ions. Now, these electrostatic forces of attraction act in all directions within the lattice, and they can be represented in several different ways. They can be represented in a 3D structure, or using a ball and stick approach instead. For ionic compounds, we can work out the empirical formula from a diagram. To do this, all we need to do is to count the number of each type of ion and work out the lowest common ratio. Well, in case you're wondering what an empirical formula actually is, it's the simplest whole number ratio of atoms or ions within a structure. Let's have a look at this example here. So I can see that the pink ions are sodium plus and the blue ones are Cl minus. I can count in this diagram I have 6 Na plus and 6 Cl minus ions. This is a 6 to 6 ratio, which simplifies down to a 1 to 1 ratio. Therefore, we can say that the empirical formula of this compound is Na1Cl1, or just NaCl. Now we can represent ionic compounds in many different ways, and there are limitations to these different types of diagrams that we use to represent them. For a dot and cross diagram, it's very helpful because it shows the transfer of electrons. But the disadvantage is that it doesn't show how the ions are arranged in 3D space, and it also doesn't show the relative sizes of the ions. With a 3D ball and stick, an advantage is that it shows the arrangement of ions in 3D space. However, the disadvantages includes the fact that it uses sticks for bonds, which is misleading, because instead the forces of attractions act in all directions. In the 2D diagram, we can see the arrangement of ions in one layer. However, it doesn't show the different layers of ions, and it also doesn't show the 3D arrangement in space. Finally, the 3D diagrams show the 3D arrangement in space, which is an advantage. However, the disadvantages include the fact that it is not to scale and it gives no information about the forces of attraction between the ions. We need to know the properties of ionic compounds. So ionic compounds have the following properties. They have high melting points, high boiling points, they conduct electricity when melted, molten, or dissolved in water, and they do not conduct electricity when in the solid state. So why is it that ionic compounds have high melting or boiling points? This is because there are strong electrostatic attractions between the oppositely charged ions. Therefore, we need a large amount of energy to overcome these forces of attraction. We also need to know why ionic compounds conduct electricity when molten or dissolved in water. Now, this is because the ions are free to move and the charge can flow freely. And this is the same reason why a solid does not conduct electricity. A solid ionic compound does not have ions which are free to move, and therefore the charge cannot flow freely. Let's have a look at covalent bonding. What is a covalent bond? We need to know that a covalent bond is a bond formed when electrons are shared between non-metal atoms. Covalently bonded substances can have different structures. We can see them as small molecules, for example H2O or O2 or CO2, or as giant covalent structures, for example diamond and silicon dioxide. We can use dot and cross diagrams to show covalent bonding. When drawing dot and cross diagrams, remember we only draw the outermost shell of electrons. Now the electrons of one atom are represented by dots and the electrons of the other atom are represented by crosses. And when we show dot and cross diagram with covalent bonding, we have overlapping regions. And these overlapping regions show the sharing of a pair of electrons. This is a covalent bond. Sometimes two pairs of electrons are shared, and this would be a double covalent bond. And occasionally we even get 3 pairs of shared electrons, which would be a triple bond. And here you can see this example of chlorine, each of which have 7 electrons in their outer shell. They both need to gain 1, so what they do is they share 1 of their own electrons and therefore gain 1 from the other as well, resulting in our covalent bond. Let's have a go at another example. Let's draw a dot and cross diagram to show the bonding in CH4. But we should know that carbon's in group 4, so it has 4 electrons in its outer shell. And we should also know that hydrogen has one electron in its outer shell. Well, if each of these hydrogens shares its electron with the carbon, then that means each of the hydrogens end up with 2 electrons and get a full outer shell. And the carbon ends up with 8 electrons, and that also has a full outer shell. So here we can see that there are 4 covalent bonds in the bonding of CH4. Substances with giant covalent structures are solids with very high melting points. Now, all atoms in a giant covalent structure are bonded to other atoms by these strong covalent bonds. Now, some examples of giant covalent structures include diamond, graphite, and silicon dioxide. We need to know that giant covalent structures have very high melting points. We need to know why this is. We need to know that this is because the many strong covalent bonds between atoms must be broken in order to melt or boil it. This requires a lot of energy. We also need to know why most giant covalent structures do not conduct electricity. This is because there are no delocalized electrons or ions that are free to move to carry charge through the structure, with the one exception of graphite, which we will learn about in more detail later. Small molecules are usually gases or liquids, and therefore they have relatively low melting and boiling points. So some examples of small molecules include water, Cl2, oxygen, anything that you're used to being a gas or a liquid at room temperature. So when boiling or melting substances made up of these small molecules, the weak intermolecular forces between the molecules get overcome. We're not actually breaking those strong covalent bonds, just these weak intermolecular forces. Now, relatively speaking, this doesn't require much energy at all. And this explains the relatively low melting and boiling points. Now we need to know that as the molecules get bigger, they have stronger intermolecular forces. So as a result, bigger molecules have higher melting and boiling points. Now we should also know that small molecules do not conduct electricity, and the reason for this is the fact that they have no charge. What are polymers? So we need to know that polymers are very large molecules made up of many repeating units joined by covalent bonds. Now the polymer chains themselves are held together by intermolecular forces. And of course, because polymers are such long molecules, those intermolecular forces are relatively strong. Now the result of this is that polymers have higher melting points compared to smaller molecules, and therefore they're generally solids at room temperature. Now, a good use of polymers is to make plastics. Now, an example of a polymer is polyethylene, and we can represent this in different ways that we need to be able to recognise. So it can be represented in this very long way here, which shows a short section of the polyethylene polymer. It actually contains thousands of these atoms, but of course we're just showing a short section which still looks pretty long. Notice those open ends to show that it's continuing onwards. Or instead, we can do it in this abbreviated form, where the little n represents how many of these repeated units we have, and n is going to be a very large number. We can represent covalent compounds in many different ways. However, there are limitations to using different types of diagrams to represent them. So, dot and cross diagrams. An advantage to this is that we can see the transfer of electrons, and we can see which atom the bonding electrons come from. However, disadvantages include the fact that it doesn't show how the atoms are arranged in 3D space or show the relative sizes of the atoms. Next up, the 3D ball and stick. This is good because it shows the arrangement of atoms in space as well as the shape of the molecule. However, disadvantages include the fact that it uses sticks for the bonds and it doesn't show that the bonds are forces. The atoms are placed far apart from each other, but in reality the gaps are much smaller. So now the 2D diagrams. Now some advantages to this is that it shows what atoms are in a molecule and how they're connected. However, disadvantages are that it doesn't show the relative size of the atoms and the bonds, and it also doesn't show the 3D arrangement in space. Finally, the 3D diagrams. Obviously, an advantage is that it shows the 3D arrangement in space. However, disadvantages include the fact that the 3D diagrams aren't to scale and it gives no information about the forces of attraction between the atoms. Let's describe the structure and bonding in diamond. This is a very common question. We should know that diamond is a giant covalent structure and every carbon atom forms 4 strong covalent bonds with other carbon atoms. Make sure you include the number of covalent bonds and the fact that they're strong. So a very common question asks us, why is diamond so hard? To answer this, we're going to say that it's a giant covalent structure, that every carbon atom forms 4 strong covalent bonds with other carbon atoms, and therefore it requires a lot of energy to break. Another very common question is, why does diamond not conduct electricity? And the answer to this is similar. Every carbon atom forms 4 strong covalent bonds with other carbon atoms, and so as a result there are no delocalized electrons or ions free to move and carry that charge. We need to be able to describe the bonding and structure in graphite. So we should know that graphite is made of only carbon atoms. We should know that it forms hexagonal rings arranged in layers. And we need to know that each carbon atom forms strong covalent bonds with only 3 other carbon atoms, not the 4 that it potentially could with its 4 electrons in its outer shell. Now this, as a result, leaves carbon with 1 spare electron, and this electron gets delocalized and is free to move through the layers. A very common question we're going to get is, why does graphite conduct electricity? So the answer we want to give is that each carbon atom has 1 spare electron which is delocalized and free to move and carry electrical charge through the layers. Another question we need to be able to answer is, why is graphite slippery? And so why can it be used in lubricants? The reason for this is that it has layers which have weak intermolecular forces between them. Now these weak intermolecular forces don't require much energy to overcome, therefore making them slippery. Now let's have a look at graphene. What is graphene? Graphene is a single layer of graphite, and its properties make it useful in electronics and composites. So let's have a look at those properties then. So it's got strong covalent bonds between the carbon atoms. A result of this is that graphene is going to be very strong, and it's going to have high melting and boiling points. Now this is because it's going to take a lot of energy to break those strong covalent bonds. If we look at the diagram, we can see that each carbon atom in graphene is only bonded to 3 other carbon atoms. We should know that as carbon has 4 electrons in its outer shell, it can form 4 bonds. And the fact that graphene only forms 3 bonds per carbon atom shows that we're going to have a delocalized electron which is free to move and carry charge, meaning that graphene is a conductor of electricity. What are fullerenes? Fullerenes are molecules of carbon atoms which have hollow shapes. The structure of fullerenes is based upon hexagonal rings, although we can sometimes have rings with 5 or 7 carbon atoms. At this level, they'll generally be hexagonal rings. So fullerenes can be arranged as a tube, for instance a nanotube, or as a ball such as Buckminster fullerene C60. Carbon nanotubes are cylindrical fullerenes with very high length to diameter ratios. This means that they have a high tensile strength and so are difficult to break, and they're useful for nanotechnology, electronics and materials. Buckminster fullerene, however, is a molecule made of 60 carbon atoms covalently bonded into a spherical shape. They have weak intermolecular forces between the molecules, which gives it a low melting point and making it slippery. Now that makes it perfect for use as a lubricant and for drug delivery. Let's have a look at metals. Now metals have giant structures of atoms with strong metallic bonding. Now this means that most metals have high melting and boiling points, and this is because it takes a lot of energy to overcome these strong bonds. Now let's have a think about pure metals. Now in a pure metal, the atoms are arranged in layers. These layers are able to slide over each other, And this means that pure metals can be bent and shaped. They're malleable. Now, a side effect of this, though, is that pure metals can be too soft. Now, a way of remedying this is we can perhaps make an alloy. An alloy is what we get if we mix pure metals with other elements. Now, the way that this works is that atoms of different elements have different sizes. Now, by mixing these together, this distorts the layers. And the layers can't slide over each other as easily anymore. We need much more force for them to slide over each other. Now, the result of this is that alloys are harder and stronger than pure metals, making them much more useful for certain jobs than pure metals. We need to know that metals are made up of giant structures of atoms arranged in a regular pattern. The electrons in the outer shell of the metal atoms are delocalized, forming metal ions. Now, these delocalized electrons are now free to move through the layers of the metal ions. So, why is it that metals can conduct electricity? The reason for this is that the delocalized electrons are free to move between the layers and carry their charge. Why are metals good conductors of thermal energy? This is because the delocalized electrons transfer energy. And finally, let's ask ourselves, what causes metallic bonding? This is due to the sharing of delocalized electrons. We need to know about nanoparticles. Well, what are nanoparticles? Nanoparticles are particles which are between 1 and 100 nanometers in size, made up of a few hundred atoms. We need to know the relative size of a few different particles. We need to know that atoms are around the size of 1 times 10 to the minus 10 meters. Nanoparticles are between 1 times 10 to the minus 9 and 1 times 10 to the minus 7 meters. Fine particles, which we may see represented as PM 2.5, are between 1 times 10 to the minus 7 and 2.5 times 10 to the minus 6 meters. And finally, coarse particles, which are PM10, are between 2.5 times 10 to the minus 6 and 1 times 10 to the minus 5 meters. Now, we need to know a few uses of nanoparticles too. We'll see that they can be used in medicine, electronics, cosmetics, sun creams, deodorants, and catalysts. Now, the main reason why they're used in so many places is because they have a large surface area to volume ratio. However, as well as being useful for this fact, there are also some risks associated with using nanoparticles. Firstly, they can be breathed in because they're so small. They can enter cells, they can catalyse harmful reactions, and also there's a chance that toxic substances could bind to them due to their large surface area to volume ratios. Now let's explore this surface area to volume ratio in a bit more detail. Let's work out the surface area of a 1 centimetre cube. We know that there are 6 faces, and each of those faces has an area of 1 times 1. So the surface area of this 1 centimetre cubed is 6 centimetres squared. Now if we work out its volume, we do 1 times 1 times 1, which gives us 1 centimetre cubed. So now if we need to get the surface area to volume ratio, we simply divide the surface area by the volume. So in this case, that is 6 divided by 1, which gives us 6. Now let's do exactly the same for a 10 centimetre cubed. 6 for the 6 faces, times by 10 times by 10, which is the area of one face, gives us 600 centimetres squared for the surface area. Now the volume will be 10 times 10 times 10, which gives us 1000 centimetres cubed. Now working out the surface area to volume ratio again, by doing surface area divided by volume, we get 600 divided by 1000, which gives us 0.6. So what we can see here is that the smaller the particle, the bigger the surface area to volume ratio. So we can see that if we increase the size of a cube by a factor of 10, we actually decrease the surface area to volume ratio by a factor of 10 too. The law of conservation of mass is an important one in chemistry. We need to know what it is. So it states that no atoms are lost or made during a chemical reaction, and that the mass of the products is equal to the mass of the reactants. And if we had a balanced symbol equation, we'll see that the number of atoms of each element is actually the same on both the reactant and the product side of this equation. So let's have a look at this in practice. We can have nitrogen, and then we can add 3 hydrogen molecules, and we end up making 2 ammonia molecules. See here that we have 2 of those green nitrogen atoms on both the left and the right hand side, and you have 6 of those pink hydrogen atoms on again both the left and the right hand side. Now that is showing that no atoms are lost or made during that chemical reaction. And we can also see this in terms of mass. So if we had 14 grams of nitrogen and it reacted with 3 grams of hydrogen, we would end up making 17 grams of ammonia. So the mass of the products is equal to the mass of the reactants. Now we know that mass is always conserved. However, it might not always look like it is. Now this is going to depend on if we have an enclosed system, like this one on the left-hand side, or a non-enclosed system. So in an enclosed system, the mass will be observed to be conserved because everything is contained and nothing escapes. Whereas in a non-enclosed system, gases can enter and leave the system. Now this may mean that the mass may appear to have changed, whereas actually all that's happened is some gases may have escaped from the system so that they can't be measured. However, it's important to know that that mass is still there and the mass has been conserved. We need to be able to name ionic compounds. We should realise that when a name ends in "ide", it's because the compound only contains 2 elements. An example of this is sodium sulfide, which just has sodium and sulfur in it, or calcium oxide, which just has calcium and oxygen. Now, if we have a name ending in "ate", however, this means that the compound contains 3 or more elements, including oxygen. So examples of this are sodium nitrate, which has the formula NaNO3, or calcium sulfate, which has the formula CaSO4. Now we also need to know how to write these formulas. And to be able to do this, we really have to know the formulas of these ions. So we need to know that the carbonate ion is CO3 2-. That enables us to write the formula of things such as calcium carbonate. So we know calcium is Ca2+. So we've got a balance between the charges there. We've got the Ca2+ and the CO3 2-. So we can just smush them together and we get CaCO3. Then we've got the nitrate ions, which are NO3-. This means if we want to write the formula of something, calcium nitrate for example, we've got Ca2+ for the calcium, NO3- for the nitrates, which we don't have a balance there. We need an extra nitrate. We need 2 of these negative nitrates to balance with the Ca2+. So in that case, the formula will be CaNO3 in brackets with a 2. So the other 2 that we need to know are the sulfate ion, which is SO4 2-, and the hydroxide ion, which is OH-. And the same rules will apply when we want to work out the formulas of different sulfates and hydroxides. Quite often, if we have a chemical reaction, we can write them in terms of ions. Let's have a look at this example where the more reactive ion reacts with copper sulfate. A displacement reaction takes place, and copper and iron sulfate are formed. Well, this can be written as an ionic equation. You might be wondering how we can do this. Well, what we do is if we look at all of the aqueous substances in our earlier equation, if we break those down into their respective ions, that's going to be our first step here. So we've got the Fe, which was a solid, we left that as it was. The copper sulfate, which was aqueous, we've broken down into Cu2+ and SO4 2-. It's important we know the formula for that sulfate ion. Then on the other side, copper, which is a solid, we just leave as it is. But the aqueous iron sulfate, we're going to break down again into its respective ions, in this case into Fe2+ and SO4 2-. So this is where the clever bit comes in. This is our next step. When an ion is on both sides of an equation, we have a spectator ion. And spectator ions are doing absolutely nothing, so we can just cancel them. So we're just going to strike through the sulfate on each side, leaving us with our ionic equation, which is Fe solid plus Cu2 plus aqueous makes Cus plus Fe2 plus aqueous. And that is it. That's how we get our ionic equations. So when we have an ionic equation like this, we can actually split it into two half equations. Let's start off by just looking at iron. So here, the Fe solid has lost 2 electrons to become the Fe2 plus ion. And so we can write this as Fe goes to Fe2 plus 2E minus. And because the iron has lost 2 electrons, remember OILRIG, we can say oxidation is the loss of electrons. So we know that the iron has been oxidized. On the other side, if we have a look at what's left here, so the copper part of the equation, we can see that those copper 2+ ions must have gained 2 electrons to just become copper. So our half equation will be Cu2+ plus 2 electrons makes copper. So here we have another half equation, and we can see that the Cu2+ ion has gained 2 electrons. Now this means that the Cu2+ has been reduced. Again, using our OILRIG, reduction is gain of electrons. In chemical equations, we represent the different states of matter using the following symbols. So a solid is represented with an S in brackets, a liquid is an L in brackets, gas is a G in brackets, and an aqueous solution is represented with an AQ in brackets. So the mass of 1 mole of a substance in grams is equal to its relative formula mass. So if we had 1 mole of hydrogen atoms, that would weigh 1 gram. If we had 1 mole of oxygen molecules, so O2, that would be equal to a mass, 2 times 16, 32 grams. Finally, if we think about having 1 mole of water, the relative formula mass of water is 18, and so the mass of 1 mole of water is 18 grams too. Now, a lot of people get very confused about moles. They think it's something really complicated and fancy, but it's just a word to represent a really big number. There's a word that we use all the time which has a similar job, and that's dozen. So we often say, oh, we've got a dozen eggs or something else, and everybody knows that means we have 12 eggs. Likewise, if we had 3 dozen eggs, we know that that's 3 times 12, 36 eggs. Now, moles do that same job, except it's a really horrible number, okay? So if we have 1 mole of a substance, we have 6.02 times 10 to the 23 particles. If we have 2 moles of a substance, then we have 2 times 6.02 times 10 to the 23 of those particles. So just don't overthink this concept, okay? So when we talk about this 6.02 times 10 to the 23, that's just talking about particles. Now that could be atoms, it could be ions, it could be electrons, it could be anything, okay? It's just representing that much stuff. And we call this number Avogadro's constant. So putting this into practice quickly, we may be asked how many molecules of water are there in 5 moles of water? Well, we should know that in 1 mole of water, we have Avogadro's number molecules of water. We have 6.02 times 10 to the 23 molecules of water in 1 mole. So if we have 5 moles, all we need to do is just times that by 5. And that ends up giving us 3.01 times 10 to the 24 molecules. We can calculate the mass of a substance if we know how many moles there are. So let's remember what we said. The relative formula mass is equal to the mass of 1 mole of a substance. So we can use this fact to turn it into a little equation. We can say that the total mass is equal to the relative formula mass times by the number of moles. And we can learn this in shorthand. Relative formula mass is often referred to as MR. And so we can say that mass equals Mr. Moles. It's a short, snappy way of remembering it. So we might be asked to find the mass of 0.5 moles of ammonia with a relative formula mass of 17. So in this case, we can use that same formula. Mass equals relative formula mass times moles, or mass equals Mr. Moles. So the mass will equal 17 for that relative formula mass, times by the 0.5 for the moles. And that gives us 8.5 grams. Now when we have a balanced equation, it shows us the number of moles that react together and the number of moles of products formed. So the balanced equation gives us the ratio of moles in a reaction. So for this reaction here, I can see that I have 1 mole of nitrogen reacting with 3 moles of hydrogen and making 2 moles of ammonia. So we can use these balanced equations to work out the mass of one of the reactants or products, so long as we know the mass of one of the others. Let's take a look at this question here. How much ammonia can be made if you have 42 grams of nitrogen and an excess of hydrogen? So there's 3 steps to take here. First, let us work out the number of moles of nitrogen. So we should now know that when working out the number of moles, moles is the mass divided by the relative formula mass. So let's work out the relative formula mass of the nitrogen then. N2 is going to be 2 times 14 because the relative atomic mass of nitrogen is 14. So the MR of nitrogen is 28. And so the moles are equal to 42, because that's the mass of nitrogen, divided by 28. And that gives me 1.5 moles. So now we know this, we're on to step 2. Here we want to use the ratio to work out the number of moles of ammonia. So here I can see I have 1 mole of nitrogen for every 2 moles of ammonia. So this is a 1 to 2 ratio. So to work out the number of moles of ammonia, we simply need to do 2 times 1.5. And that gives us 3 moles of ammonia. So now on to that last step. Now we need to work out the mass of ammonia. Let's use the equation that states that mass equals Mr. Moles. So we need to get that MR, or relative formula mass of ammonia. Of course, there's 1 nitrogen, so we've got 14, plus 3 times 1 for the 3 hydrogens. And that gives us an MR equal to 17. So in this case here, we're going to say that the mass is equal to that relative formula mass, 17, times by 3. And that gives us a mass of 51 grams. So here the answer is 51 grams of ammonia can be made if you have 42 grams of nitrogen. So in a chemical reaction that has 2 or more reactants, in all likelihood, one of the reactants is going to run out before the others. And we call this a limiting reactant. And the remaining reactant that hasn't run out yet is said to be in excess. Now, the amount of limiting reactant that we have is going to affect the maximum mass of products that are made, because once that limiting reactant runs out, the reaction stops. Let's look at this example here. 15 grams of nitrogen is reacted with an excess of hydrogen. Calculate the maximum mass of ammonia made. So the first thing we need to do here is to write a balanced equation, and they may well give this to you in the exam anyway. So here we have N2 plus 3H2 goes to 2NH3. But like I say, they may well give this to you in the exam. So we know we have 15 grams of nitrogen, and we're looking at the mass of ammonia made. That means that those are the only 2 bits we care about in this equation. I'm going to use my grid method here. I've got 3 rows. I've got mass, the relative formula mass, or the MR, and the moles. And I'm filling in the information I know. I know that we have a mass of 15 grams of nitrogen to begin with. And you may find in the exam they give you the relative formula mass of all of these substances. Here, let's work it out though. So nitrogen is 2 times 14, which is 28. So to calculate the moles, we've got moles is mass divided by the relative formula mass. And I like this grid method because it's just the 15 over the 28. Now that gives me 0.5357. That's the number of moles of nitrogen we have. But in this question, we're not being asked about nitrogen, we're being asked about ammonia. And this is where that balanced equation that they will probably give you will help you. Here we can see we have a 1:2 ratios. So if we had 1 mole of nitrogen, we have 2 moles of ammonia. If we have 0.5357 moles of nitrogen, we have 2 times 0.5357 moles of ammonia. And putting this into my calculator, I find that I have 1.0714 moles of ammonia. So we're nearly there now, okay, just following through our grid method. We need to have the relative formula mass of ammonia now. Again, they may well give this to you in an exam question, but let's work it out. 14 for the nitrogen plus 3 times 1 for the hydrogen gives us 17. So let's fill that in here. So 17. And of course, we need to find the maximum mass made. And that's assuming that 1:2 ratio. So if we use that number that we found, and the fact that mass equals Mr. moles, or the relative formula mass times moles, we end up getting a maximum mass of ammonia made equal to 18.21 grams. And that's our answer. So the method that we used there is we worked out moles of one of the things that we needed, used molar ratios, and then used the new moles to calculate the mass of that final substance. Energy is always conserved in chemical reactions. What this means is we can never create energy or destroy it, but in fact the total energy in the universe before a reaction takes place is exactly the same as the total energy in the universe after the reaction takes place. So if we have a chemical reaction which is transferring energy to the surroundings, such as a combustion reaction, then the molecules of the products produced must have less energy than the reactants did before that reaction. Now, this deficit of energy between the products and the reactants should equal the energy that's been given out to the surroundings. Now, when we're talking about energy transfers, we've got 2 different types of chemical reactions. There's exothermic reaction and endothermic reactions. Let's start off by having a look in a bit more detail at exothermic reactions. So we need to know what is an exothermic reaction. This is a reaction which transfers energy to the surroundings, and we see the temperature of the surroundings increase. If we break down that word exothermic, thermic is referring to heat energy, just like the word thermometer, and exo is referring to energy exiting, and that's one of my top tips, as you can see here. So we've got some examples of exothermic reactions that we should be familiar with. Combustion is an example, oxidation reactions, and also neutralisation, as well as us having everyday uses such as hand warmers that we might use in our coats in the winter, and also self-heating cans, which would be great if we're going out camping and we just want a way to get a hot meal in us. So for exothermic reactions, make sure you know those examples and make sure you understand that definition of an exothermic reaction. Now let's have a look at endothermic reactions. We need to know that endothermic reactions are reactions which take in energy from the surroundings, and so the temperature of the surroundings decreases. Again, if we deconstruct that word, we've got thermic, which is referring to that heat energy, and the endo is referring to the energy entering. Again, little top tip below here to help you remember. Just like with exothermic, we need to know a couple of examples of endothermic reactions. So these are a little bit more technical and less everyday. We've got thermal decomposition, that's one example. And another reaction is the reaction between sodium hydrogen carbonate and citric acid. So some everyday examples of an endothermic reaction include some sports injury packs. So we can use these if we have an injury and we want to cool down the area. We can use one of these sports injury packs and it would cool down. It's important that we know how we can investigate the variables that affect temperature change. And this is one of your required practicals in the course. As we should know, there's several different chemical reactions that can either be exothermic reactions or endothermic reactions. I'm not going to go through all of these, I'm just going to have a look at the neutralisation reaction that takes place between hydrochloric acid and sodium hydroxide. So if we want to investigate this, let's start off by measuring 30 centimetre cubed of hydrochloric acid and transferring it to a polystyrene cup. Now, that measurement could change depending on what you're given in the exam. However, the importance of the polystyrene cup is the fact that polystyrene is an insulator. It's going to prevent heat loss. So let's stand this cup in a beaker to stabilise it so that it doesn't fall off. And let's use a thermometer to measure the initial temperature of the acid. Now this is really important if we need to get the temperature change, if it's increased or decreased. We need to know where it started. So let's record that temperature. And now let's measure a certain amount of sodium hydroxide. Here I suggest 5 centimetres cubed. And let's use a measuring cylinder to do this. Now let's add this to the polystyrene cup. Let's place a lid on the cup with the thermometer still in the solution. Now the reason why we've placed this lid on the cup is going to be to insulate it, because when heat energy is given off to the surroundings, it could escape into the air, leave the system, and then the thermometer won't measure that change. So now let's stir using the thermometer. This is going to ensure that the heat is evenly distributed through this solution. Now let's wait, and let's wait until we reach a maximum temperature. So keep taking measurements at regular intervals and you'll notice eventually we reach a maximum, and note that down. Now let's repeat this experiment and find the mean maximum temperature reached. Once we've done that, let's finish off by repeating for different volumes of sodium hydroxide, for instance going up in 5 centimetre cubed intervals. Remember, the whole point of this is we're investigating the variables that affect temperature change. So in this case, we're going to investigate the effect that different volumes of sodium hydroxide is going to have on that temperature change. We need to understand that when we carry out an investigation like this, we need to know the independent variable, the dependent variable, and the control variable. I like to remember that the independent variable is what I change. So it begins with an I, it's what I change. And we have changed the volume of sodium hydroxide. So that's our independent variable. Now the dependent variable depends on what you did. And it's the thing that you measure. In this case, we know that we're measuring the maximum temperature of the solution. So that is going to be our dependent variable for this particular experiment. The control variable is what we keep the same each time. And in this case, we've kept the volume of the hydrochloric acid the same. So that is our control variable. Now in these questions, we always need to be able to identify what sources of error there were. And in this case, the biggest source of error is going to be due to unwanted heat transfer. And this is why we did certain things in this experiment, like placed it in a polystyrene cup, which is an insulator, and placed a plastic lid on the top, again an insulator, to prevent and minimise those heat losses to the surroundings. Finally, we generally want to have a think about what do we learn from the practical. And what we would have observed is that up to a point, as we increased the volume of sodium hydroxide, the temperature change would have increased. And we should understand that the bigger the temperature change, the more energy has been absorbed or released, depending on what your investigation was about. But there we have it, okay? That is your investigation into temperature changes that you need to know about. We need to make sure that we're really familiar with reaction profiles, what they look like, and what they represent. So reaction profiles can be used to show the relative energies of reactants and products, the overall energy change of a reaction and the activation energy. If we look at this exothermic reaction, we can see that the reactants have more energy than the products, and energy is released as we go from our reactants to our products. Our activation energy is represented by the difference in energy between the reactants and the peak of this curve. Now, endothermic reactions, on the other hand, we know take in energy. And so here we can see that the reactants have less energy than the products. And that's because energy gets absorbed to give us the energy of the products. The activation energy, again, is represented from the difference in energy between the reactants and the peak of this curve. Well, what is activation energy? We need to know that activation energy is the minimum amount of energy that particles must have to react. During chemical reactions, energy gets taken in to break the bonds in the reactants, and energy is released to form the bonds in the products. Therefore, we can work out the overall energy change of a reaction. To do that, we just need to find the sum of the energy needed to break all the bonds in the reactants and subtract the sum of the energy released when forming all of the bonds in the products. As a result of this, we can say that during exothermic reactions, the energy released when forming new bonds is greater than the energy needed to break existing bonds. And this, of course, explains why energy is released to the surroundings during an exothermic reaction. Well, at the same time, we can say for an endothermic reaction, the energy needed to break the existing bonds is greater than the energy released when forming new bonds. And that's why during endothermic reactions, they take in energy from the surroundings. Now, we might find that we need to do some calculations. Here, let's look at this example. So methane combusts in oxygen to form carbon dioxide and water. The reaction is shown below. Calculate the energy change for the reaction. So notice here that all of the bonds are shown. If instead you were just given a balanced equation, you would need to write this out just like I have here. And if there's any balancing numbers like a big 2 in front of the oxygen, then make sure you write those down twice, just like I have here. Notice also on the right-hand side, we've got this little table which has the bond energies of all of the different bonds that we're going to see in this question. Well, of course, we know that to calculate the overall energy change of a reaction, we need to work out the sum of the energy needed to break the bonds in the reactants, and then we need to take away the sum of the energy released when forming bonds in the products. So let's have a look at how we calculate this. Let's start by just looking at the reactants. So starting off here, I can see that in the methane, I have 4 CH bonds. So looking at the table, I can see that each bond is 412 kilojoules per mole. So I'm going to do 4 times 412. Now I can see I have 2 O double bond O's. And so again, looking at the table, I want to do 2 times 498. Now let's put that into the calculator to simplify. So that ends up equaling 2,644 kilojoules per mole. So now let us have a look at the products. So here I can see I have 2 C double bond O's in the carbon dioxide. So from our table here, I can see I need to do 2 times 743. Now onto the waters, I can see that I have 1, 2, 3, 4 OH bonds. So here I'm doing 4 times 463. Now, if I pop that into the calculator now, I end up getting the energy released when forming bonds in the products, and that is 3,338 kilojoules per mole. So let's have a look here then. I know that to get the overall energy change of the reaction, I need to take the energy from those reactants and take away the products. So breaking minus making is how I always think about it. So 2,644 minus 3,338 gives me minus 694 kilojoules per mole. And that is how we would do one of these questions in the exam. So let's summarise here what we know about breaking bonds and making bonds. So when breaking bonds, we know that heat energy is taken in, we know that the temperature of the surroundings will decrease, and we know that this is an endothermic reaction. Forming bonds, on the other hand, we know that heat energy is given out, we know that there's going to be an increase in the temperature of the surroundings, and we know that this is an exothermic reaction. When metals react with oxygen, they form metal oxides. This is called an oxidation reaction. So an example here is when magnesium reacts with oxygen, forming magnesium oxide. Now reduction, on the other hand, happens when we remove oxygen from a metal oxide. For example, the reaction between copper oxide with carbon to form copper and carbon dioxide. Now we can summarise this. So oxidation will involve a gain of oxygen, and reduction will involve a loss of oxygen. We already know about oxidation and reduction. We know that oxidation involves the gain of oxygen, and reduction is the loss of oxygen. However, we also need to know about them in terms of electrons. We need to know that oxidation is the loss of electrons, and reduction is the gain of electrons. We've got a great little mnemonic here to help us out. So OILRIG. Oxidation is loss of electrons and reduction is gain of electrons. So let's have a look at this little summary here to help us know the difference between oxidation and reduction. So oxidation is the gain of oxygen. I always think that kind of makes sense. Oxidation, you're gaining oxygen. Reduction, on the other hand, means getting rid of something. You're getting rid of that oxygen. However, in terms of electrons, there's nothing about the name oxidation that links with electrons really, does it? And that's where OILRIG comes in. Oxidation is the loss of electrons, reduction is the gain of electrons. We need to know what ions the acid produce in aqueous solution. So this is such an easy mark if you just learn this one fact. So acids produce hydrogen ions. We also need to know what ions alkalis produce in aqueous solution. This is again such an easy mark, so please do learn it. It's hydroxide ions. We also need to know how we can measure the pH of a solution. So we could use one of two methods. The first method is universal indicator. We should know that when we add a universal indicator to a solution of an acid or alkali, or even a neutral solution, we will observe a colour change. However, this is quite an approximate answer. You're not going to get a number or anything, are you? You're just going to get a rough idea if it's an acid or an alkali or neutral. Now, a pH probe is the other method we could use. And this is great because this is an exact method. This will tell us the pH of our solution. So the pH scale ranges from 0 all the way up to 14. And if we were to add a universal indicator, we can see this colour scale. We can see that when we have a strong acid, so somewhere around the range of 0 or 1, the universal indicator will change to red. When it's neutral, the universal indicator will show you a green colour. And of course, when it's very alkaline, say 14 pH, we will see a dark purple colour. So we should know, of course, that in terms of pH, a neutral solution has a pH of 7, an acid has a pH less than 7, and an alkali will be more than 7. So neutralisation is the reaction that takes place between an acid and an alkali. And we need to know the ionic equation that takes place when we have a neutralisation reaction. This is such a simple one when you think about it. We've got the H plus from the acid plus the OH minus from the alkali, which go together and make water. So make sure you learn this. In chemistry, it's very important that we know about 3 main acids: hydrochloric acid, sulfuric acid, and nitric acid. We need to know that the formula for hydrochloric acid is HCl. And we need to know that when that is put into water, into solution, it will dissociate to form H plus and Cl minus ions. With sulfuric acid, we should recognise that that has the formula of H2SO4, and again, when that's in solution, it forms H plus and SO4 2- ions. Nitric acid, on the other hand, has the formula HNO3, and that will dissociate to give the ions of H plus and NO3 minus. Now you might be wondering why this is so important, but whenever we need to write formulas for certain things, we need to know these ions to get the formula correct. We also need to know that acids and metals can react. So metals will generally react with dilute acids to form a salt and hydrogen. That's the MASH acronym. So metal and acid makes a salt and hydrogen. Now, we've looked at how metals react with acids, but we also need to know what type of reaction this is. We need to know that this is an example of a redox reaction. But what is a redox reaction? We need to know the definition that a redox reaction is a reaction where both reduction and oxidation occur at the same time. So let's look at an example to put this into action. The ionic equation for the reaction of zinc with hydrochloric acid is 2H plus Zn for zinc goes to Zn2 plus H2. Now if we split this into two half equations, let's start by having a look at the 2H plus goes to H2. Now in order for that to happen, it must have gained two of these negative electrons. Using OILRIG, we know that oxidation is loss, reduction is gain of electrons. So here we can say that the H plus has gained electrons and been reduced. Now, on the other hand, if we look at the zinc, we know zinc goes to zinc 2 plus. In order to form the 2 plus ion, we must have lost 2 electrons. And so those zinc atoms have lost electrons, and using OILRIG again, oxidation is loss. We can say that the zinc atoms have been oxidized. So we can see here that in this reaction between zinc and hydrochloric acid, both reduction and oxidation have occurred in that same reaction, and so it's a redox reaction. We also need to learn about how acids can be neutralised and produce salts. So there's a few different reactions that can take place which are neutralisation reactions. So acids can be neutralised by alkalis, which are soluble metal hydroxides like sodium hydroxide, by bases such as insoluble metal hydroxides and metal oxides like calcium oxide, and metal carbonates like calcium carbonate. So it's very important we get memorising these two reactions. So we need to know acid plus the metal carbonate makes a salt plus water plus carbon dioxide. And we also need to know that an acid plus a metal hydroxide or an oxide makes a salt and water. Now, different acids are going to produce different types of salt. And this is really important we know this so that we name the correct salt in a question. So if we ever have hydrochloric acid in our reaction, we're going to make a chloride salt. Sulfuric acid is going to form a sulfate salt, and nitric acid is going to form a nitrate salt. So let's have a look at what this is like in practice. So if we had hydrochloric acid and it reacted with calcium carbonate. Now we just said that when an acid reacts with a carbonate, we make a salt plus water plus carbon dioxide. But what salt is it? To do that, we need to look at what the metal ion is. So in this case, that's Ca2+. The salt ion in this case is going to be Cl- because we have hydrochloric acid. And so therefore, the salt will be calcium chloride. Now, we can work out the formula of this by doing our crisscross method. Okay, so I'm going to crisscross these charges, and that is going to give me CaCl2. And the whole reason for this is that we need to have the same charge of both the positive and the negative. So we need two of the negative Cl's to balance with a Ca2+. So now, if we have sulfuric acid reacting with sodium hydroxide, the metal ion is Na+, the salt ion is going to come from the sulfuric acid, that's the SO4 2-, the sulfate ion, and that's going to make us sodium sulfate. Let's use the crisscross method again, and here I can see I have Na2, SO4. Now finally, if we have nitric acid with magnesium hydroxide, the metal ion is Mg2+, the salt ion is NO3-, and the salt in this case is going to give us magnesium nitrate because we have that nitrate ion from the nitric acid. Let's use our crisscross method again, and here I can see the formula will be MgNO3, and the whole thing is times 2. So it's MgNO3 in brackets with a little 2 down below. We need to know the difference between strong acids and weak acids. So a strong acid is an acid that is completely ionized in aqueous solution. Alternatively, we may say that it's an acid fully dissociates in aqueous solution. So examples of strong acids are the classic hydrochloric acid, nitric acid and sulfuric acid. And we can show the dissociation, this ionization, using an equation. So hydrochloric acid, for instance, becomes H+ and Cl-. Now on the other hand, a weak acid is an acid that's only partially ionized or dissociated in aqueous solution. Examples of weak acids include ethanoic acid, citric acid, which we find in oranges and other citrus fruit, and carbonic acid. So we can show this using this equation. So here we've got methanoic acid, HCOOH, and then that becomes H+ and HCOO-. However, we didn't just do our normal arrow. Instead, we've done this special arrow which shows that this is a reversible reaction. Concentration tells us how much of a substance is dissolved in water. So we need to know the difference between a concentrated acid and a dilute acid. Well, if we have a concentrated acid, we've got a lot of acid in a small volume of water. So we could say that we've got a lot of acid per unit volume. Now a dilute acid, on the other hand, has a small amount of acid in that same amount of water. So we could say that a dilute acid has a small amount of acid per unit volume. And these diagrams demonstrate this. You can see that there are fewer acid molecules in that dilute acid in that same space compared to the concentrated acid. Now, at any given concentration, a stronger acid is going to result in a lower pH. Now we need to know that as the hydrogen ion concentration increases by a factor of 10, the pH will actually decrease by 1 unit. Now this can sound a bit confusing, so the best way to see this is to have a look at an example. So if we're told that the hydrogen ion concentration of an acid of pH 3 increases from 0.01 moles per decimeter cubed to 0.1 moles per decimeter cubed, and we're asked what is the new pH of the acid, here we need to recognise that the concentration is increased by a factor of 10. So using our fact above, we can say that the pH will decrease by 1 unit. Now if it started at 3, if we subtract 1 from that, we get 2. And so therefore the pH is now 2. And this is what we mean when we make that statement: as the hydrogen ion concentration increases by a factor of 10, the pH decreases by 1 unit. Electrolysis is the process of splitting up an ionic compound using electricity. When an ionic compound, such as sodium chloride, is melted or dissolved in water, its ions are free to move through the liquid or solution. Now this liquid or solution is able to conduct electricity, and we call this substance an electrolyte. Now if we place a negatively charged cathode and a positively charged anode into this electrolyte, we're going to see an electric current flow. The reason for this is the positive ions from our ionic compound are going to be attracted to the negative electrode, the cathode, and the negative ions from that solution or molten liquid are going to be attracted to the positive electrode, the anode. And this therefore completes the circuit. Now this process of separating the positive and the negative ions is called electrolysis. Positive ions end up gaining electrons from the cathode. Using OILRIG, oxidation is loss, reduction is gain, we can see that those positive ions are getting reduced, whereas the negative ions are going to lose electrons at the anode. They're going to get oxidized. Now, if we look at molten lead bromide as an electrolyte, we can see that at the cathode, those positive lead ions are going to gain electrons, forming lead metal, and over at the anode, the Br- negative ions are going to lose electrons, producing bromine. Positive ions end up gaining electrons from the negative cathode. Now remember, oxidation is loss, reduction is gain, so we can say that those positive ions have been reduced at the cathode. Now the negative ions lose electrons at the anode. Again, remembering OILRIG, oxidation is loss of electrons. We can see that those negative ions get oxidized at the anode. Now if we have a look at molten lead bromide as an electrolyte, we can see that at that negative cathode, the lead ions gain electrons, forming lead. We can see this using the Ionic equation of Pb2 plus 2 electrons makes Pb. So we've got a reduction taking place there. Whereas at the anode, the Br- loses electrons, producing bromine. Again, we can see this using our Ionic equation. So 2 Br- makes Br2 plus 2E-. So here we can see because the Br- has lost 2 electrons, it has been oxidized. So we need to know about electrolysis of aqueous solutions too. So electrolyzing aqueous solutions can be beneficial over molten substances because less energy is required. You don't need to melt down the substance, simply dissolve it. However, working out the products is a bit harder because the water in that solution is also going to break down. So that means that as well as having the ions from your ionic substance, you're also going to have the H plus and the OH- from the water. Now the products formed is going to depend on the relative reactivity of the elements. So over at that negative cathode, hydrogen is going to be produced if the metal is more reactive than hydrogen. Over at the anode though, a little bit trickier here. If halide ions are present, like chloride or bromide, the halogen will be produced. However, if no halide ions are present, then oxygen will be produced. We need to know the products of electrolysis of the following solutions. So sodium chloride, sodium sulfate, copper chloride and copper sulfate. So let's have a look at how we work out what the products are. So with sodium chloride, the positive ions in a solution of that substance will be Na plus and H plus from the water. Now the negative ions will be Cl minus and OH minus from the water. Now in terms of the products, because sodium is more reactive than hydrogen, hydrogen will be formed at the cathode, whereas over at the anode, because halide ions are present here, chlorine is going to be produced. Now in this case, we also see the Na plus coming together with the OH minus to also form sodium hydroxide. Now let's look at sodium sulfate. Now again, sodium is more reactive than hydrogen, so hydrogen will be formed at the cathode. Now, in terms of the negative ions, there isn't a halogen present. Now, as a result, because there's no halide ion, oxygen is going to form at the anode. Now, for copper chloride, we have the positive ions of Cu2 plus and H plus. Now, copper is actually less reactive than hydrogen. Therefore, we're going to form copper at the cathode. Now, for the negative ions, you can see we have a halide ion present. So we're going to make a halogen at the anode. We make chlorine. Now, for copper sulfate, again, we've got Cu2 plus versus H plus. Hydrogen is more reactive than copper, so copper is formed. And out of the negative ions, we have the sulfate ion and the hydroxide ion. Neither of those are the halides, so therefore we're going to form oxygen at the anode. And there we have it. Make sure that you give those a good practice and that you can recognise what's made in those cases. Now, when doing the electrolysis of aqueous solutions, We also need to know the ionic equations that happen at the cathode when forming hydrogen and at the anode when forming oxygen. So at the cathode, when we form the hydrogen, this one's quite simple really. We take the two H plus ions plus 2 electrons and you make H2. Now here, because the H plus ions have gained electrons, we have reduction taking place. Again, we're using our OILRIG. Now over at the anode though, it's a little bit trickier because this is all about the hydroxide ions. So you can learn one of these two reactions. You can either learn that 4OH minus goes to O2 plus 2H2O plus 4 electrons, or you could simply have those electrons on the other side and instead think of it as 4OH minus lose 4 electrons, so minus 4 electrons, to make O2 plus 2H2O. And notice these are both the same. And here you can see the hydroxide has lost electrons, therefore it has been oxidized. So make sure that you get learning these ionic equations.
Ouch! This is why in some videos I explain scratches.